I will start with a fast introduction of the European cluster of ceramics and this WebTech webinars, and then I will give you the floor to give your presentation. So this WebTech organized by the European cluster of ceramics are dedicated on ceramics technologies, process, raw material, specific ceramics and application, and also surface treatment. And they are dedicated on our markets, targeted markets that are written here in this first slide. So luxury and creation is the first one, health, environment, housing, energy and transport also, and electronics and photonics application. We also have two technological transverse application markets that are factory of the future and surface treatment. For those who are connected, please switch your microphone off so that we cannot have disturbing noise during the presentation, please. And to start, I will give you an information about a ceramic network, which is our B2B meeting events. The 4th and 5th of November, and it is held in Limoges, in the Zenith of Limoges. So if you're interested to participate, you can write to us and go on our website to have all the information that you can get on Ceramic Network. So for November. And today we are hosting a session concerning additive manufacturing of ceramics parts made by FDM process. And the speaker is Guillaume DE CALAN, CEO of Nanoe, a company member of our cluster. And in a few minutes, I will give the floor to Mr. DE CALAN to make this presentation. You can also have a look on our website, mentioned here, www.cerameurope.com, to see all the scheme that will be held by different speakers concerning data science, sintering, PDC, nanoseq, and so on. We have plenty of sessions until the end of April. So you can register if you want to connect. So it's every Tuesday and Thursday in the morning and in the afternoon, 2 sessions per Tuesday and Thursday. And some recommendation now to, before we beginning this session, switch off your microphone and camera using these icons here to have a better broadcast and to avoid also disturbing noises during the presentation. And of course, you can ask your question if you have one using the chat here. So this is this icon. You can address your question even to the speaker, Guillaume DE CALAN, or to the organizer, me, Florine Boule, or to everyone if you want to address it to all the participants. Okay, so finish for this fast introduction. I will give now the screen sharing to Guillaume.
Well, thank you very much for attending to this webinar. Today I'm going to talk a bit about ceramic additive manufacturing by FDM or FFF process. I am Guillaume DE CALAN, the CEO of Nanoe. And before we go into the subject itself, I'd just like to give a few information about the company so that you see where we come from and what is our role in 3D printing. So just a few words about the company. Nanoe, we're a raw material producer. To make it simple, our job is to make raw materials in form of powders, feedstocks, any kind of materials for production of technical ceramics. We're an industrial company. We've been active for more than 10 years now. Our main products are alumina, zirconia, and what's called ZTA and ATZ, which are composites of alumina. And again, this is an industrial scale, not a huge scale, but and we focus on ready-to-use materials. Being still a relatively young company, we were founded in 2008. We also focused a lot on innovation with a lot of new material developments, some customer-centered R&D, and we do have a new activity on 3D printing materials. As I told you, we are a raw material supplier. So here I'm going to talk about one technology, but actually we do supply raw materials for several technologies for ceramic additive manufacturing, not only for FDM. So how do you make a ceramic in general? What does our customers do with our raw materials? Well, there are always quite a few different processes for shaping ceramic, but it's always the same thing. You have a shaping process and then a sintering process. Shaping can be done usually by pressing, casting, injection molding, or by 3D printing. And we do provide raw materials for all of these processes. So powders for pressing, slurries for casting, feedstocks for injection molding, and raw materials that can be used directly in 3D printers. The application then, the main applications are semiconductor, biomedical, and wear parts and toolings. In these fields, what we do are usually high-tech raw material, high-end raw materials, most of the case for traditional shaping process, and in order to increase the wear resistance and the life cycle of the products of our customers. So now let's talk a bit about Zetamix 3D printing. So Zetamix is a brand we launched a bit more than 2 years ago now. We started working on materials for 3D printing, and we decided to launch a line of material for FDM printing. So what do we do exactly in this case? Again, we're a raw material supplier. So what we do is we prepare raw materials that are compatible with existing machines on the market. Here, FFF machines, which are used usually for thermoplastics. So how do we do that? We just make 2 steps of preparation. We do some compounding, which is a mixture of powder and binders, thermoplastic binders, and then we extrude it to make a filament. So yes, our core competences are really in the compounding part, so a mix of several binders with a ceramic or a metal powder, and then the extrusion of these very highly loaded filaments. We usually have more than 50 volume% of powder in the mix, which means something like 80 to 90% in mass, and that makes it quite difficult to mix and to extrude. And regarding the materials available, so we started with ceramic, as this is really our core business, alumina, zirconia, black zirconia, and we recently launched also a stainless steel filament for applications mainly in tooling, but I'll go back to that later on. So once you have that filament, how do you get to a dense part, to a final part? Again, it's a several-step process. It is, as I told you, any process to make ceramics, you usually have actually a shaping process, which will be here replaced by printing, and a sintering process. If you go to the beginning, you actually start with the file preparation, so that's quite straightforward. Printing, binding, sintering, and then you get the final part that you may want to post-process. I'll go in details about these different steps. The first step is file preparation. As we are using open systems, one of the good things is we don't have a specific software. We use software which are already on the market, and most of them are open source. That means we just have to download it and we can use them to prepare our files. This is a slicer called ID Maker, but you could use Cura or any other slicer on the market. With this slicer, we can see the virtual plate, so the build plate of the printer, and we are going to load the part, the STL 3D file we want to print, and the slicer is going to translate it in a set of instructions for the machine. So this is what we see here. We can see the layers, and that's really exactly the tool path that will have the machine during printing. Once we have this file, we can upload it to the machine directly or through a USB stick or whatever, and then we go to printing. Printing is really exactly the same thing as FDM and FFF printing. For those who are not familiar, FDM printing is made with a thermoplastic material. In our case, it's a mix of thermoplastic and powder in the form of filament, and this filament is pushed through a heated nozzle and melted. And we deposit the material in the melted phase, and it will cool down and make a solid part afterwards. We can also use a second nozzle to print with some support materials if we have some geometries which are not possible to print with just one material. Once we have printed, we get to the, I'd say, most complicated phase, which is debinding and sintering. Debinding, the objective of debinding is to remove all the plastic binders without damaging the part, and that's really a critical thing. Managing to remove all of the binder without having any cracks, any damage, any deformation in the part. This is usually done by a two-step debinding process. The first step is solvent extraction. We will dip the part in the solvent, in our case it's acetone, and then the thermal debinding, we put the part in the furnace, and in the furnace we will burn the rest of the binder. And then once you have burned this binder, you will have what we call a bronze part or a debinded part, which is extremely brittle and which must be sintered to get to the final mechanical properties. What happens during sintering? Sintering means going to high temperature, a bit lower than the melting temperature, but still relatively high, to get to a dense ceramic or metal. What happens during sintering is the porosity that you can see between the grains are going to be removed outside of the ceramic by solid diffusion phenomena, and the grains themselves will kind of melt together and grow to get to a dense microstructure. The typical densities we can reach with this process is up to 99% for ceramic. For metal, it's a bit lower, it's usually 90 to 95, but this is really quite good enough for most applications. Obviously, going from a porous material to a dense material means there is some shrinkage. The porosity needs to go somewhere. And it goes outside of the part, and the part will densify and shrink. Linear shrinkage is usually between 15 and 20%, which is very significant and which is something that needs to be anticipated in the file preparation, and it will also have an impact on the precision and everything. What are the key benefits of this technology? The first thing is it's a very easy to use system. If you compare it with any technology for ceramic or metal 3D printing, I'm not saying it's completely obvious, but it's much easier to launch and to get started with 3D printing. Training time for this system is usually 1 day. When we sell some machines, we take 1 day for training, and customers are ready to print some parts. It can be used by any trained technician. You don't need highly qualified people to use that. And there is very little security issues because we're not manipulating powder. We are manipulating filaments. That's really something which is quite beneficial. The investments are very low cost, and that's really one of the main things. This comes from the fact that we are using an open system. That means you can use our filaments with any kind of printers. You don't have to buy the printer from us. We can sell some printers, but if we do that, we just buy them, adapt them a bit to the filament, and resell them. But we are not a machine manufacturer. We buy machines from the market, which allows us to have an offer, a starting offer with a printer, a debinding kit, and furnace, all of this for 10,000 euros. And this is unheard of. You have no other technology that allows you to print metal and ceramic for that kind of investment cost. This is really unique. It's also a versatile technology. It is compatible with a wide range of materials. For the moment, what is available is alumina, zirconia, black zirconia, and stainless steel, but potentially any material that can be sintered could be printed by that technology. We have a lot of developments going on silicon carbide, tungsten carbide, silicon nitride. I saw someone mention fused silicate could be done also, even though it's not there yet, and some other metal. So that's really a technology that is compatible with a lot of materials. The last thing is it has a relatively good accuracy. I'm saying relatively because obviously if you compare with SLA, for instance, SLA has a better accuracy. I'm not denying it, but the accuracy should be around plus minus 0.1 millimeter, and that is on relatively big parts, up to 80, 100 millimeter. Obviously, it's also, as any 3D printing technology, interesting in terms of making complex parts, followed out structures, very low volume production, and so on. The key benefits I was stressing are mainly compared to other technologies. If we do want to compare with other technologies, here is, let's say, a small benchmark of the let's say, mainstream technologies for printing of ceramics. I know that other technology exists, but this is, I would say, the main ones: binder jetting, inkjet, SLA, and FDM. Well, the first thing is obviously FDM will rank as the first, or actually the last, the lowest cost in terms of price. This is the lowest investment cost you can find. In terms of accuracy, it's not the best, but it is relatively good. It allows you to get to dense parts, which is not the case of all these technologies, and the speed of printing is quite good. Again, everything is relative here. I'm not saying it's super fast compared to some other technologies for polymers, but for ceramic additive manufacturing, the speed is relatively good. Apart from this technology, I would say that the most mature technology is probably SLA 3D printing, which is made with resins, and where you have a few players already making machines for this technology. What are the applications? Here I'm going to present only applications about ceramic afterwards, but I just wanted to mention metal also. The number one application we have for this technology is actually tooling. That means customers are using the system to print parts that are used internally. They're not selling printed parts. There are a few exceptions, but most of them are not selling printed parts. They are making tooling for internal use. You do have a few industrial who are printing complex ceramic parts, usually for high temperature applications, parts that could probably not be made by other technologies. And then you have a bit of prototyping, which was one of the first applications of 3D printing. We do have a few customers using it as a prototyping unit. For metals, it's mainly about tooling for the moment. So, about some examples of application. I'm going to show you 4 examples, 4 use cases. 2 of them are about tooling. 1 of them is for a complex part, which would not be made in any other way. And the last one is for prototyping. So the first use case, it's an application we developed with the ESRF, which is the European synchrotron based in Grenoble. Synchrotron is a particle accelerator. Basically, it's a very big and very powerful SRD analysis equipment. Usually, this is made to analyze materials with a very wide range of temperature, starting from very low temperature down to 300 degrees C, minus 300 degrees C, I would say, up to high temperature, up to 1200, 13, 1400 degrees C. Obviously, that means that the ESRF needs sample holders, heating hold elements, gas blowers, all kinds of on-demand parts that can withstand that kind of temperature. And also, it's a lot of small on-demand parts. Each experiment needs a different sample holder, a different heating element, a different kind of sample environment in general. That means it's a lot of small, complex parts in low volumes, usually with quite urgent requirements, which is really a perfect use case for 3D printing. So what does the ESRF do with our technology? They make, for the moment, mainly 3 parts, even though some others are in progress at the moment. Some simple parts, such as heating cartridge, it's 2 pictures on the top, where you can see ceramic part which is 3D printed and heating elements. Some sample holders, which are also relatively simple. It's on the lowest side and on the left side, and then they have a future project which is a bit more complex about making some water-cooled micro furnaces. So furnace where you can go up to 1200 degrees C inside, but the wall would still be at room temperature because it is cooled by a water circuit on the outside. If you focus on the 2 first ones, which are already actually being used by ESRF, they're really being used for actual measurements. Sample holders, it's quite simple. They started because they had an experiment where the sample holder was in stainless steel, and they had a problem of heat conductivity. The stainless steel was too conductive, which meant that the samples were not at the targeted temperature. By replacing with ceramic, they managed to solve that problem, but they needed the replacement part very fast. But because the measurement was already going on and they needed the replacement as fast as possible, and they managed to reduce the part production between design, printing, binding, and sintering to 1.5 days before they could replace a stainless steel part with a ceramic part. Regarding heating cartridge, here it's a different thing. This is usually planned a bit before, so there's not so much of an emergency, but it's a lot of custom size and shapes. Every heater is different for every experiment. And so having it 3D printed is very convenient. The ESRF really adapt to every experiment. And there's also a cost-saving issue. Printing the part costs almost nothing, to be clear. And if you had to buy these heating cartridge, it would be much more expensive, especially if you want to have them on demand. So the second use case is regarding the ink preparation industry and also the ceramic industry. Actually, it's about custom impellers. We do have a few customers who required us if we could print custom-made impellers with specific shape and especially with specific size to adapt to the size of the container. There's also an issue which is to avoid tool wear and oxidation and pollution in the product. Usually the impellers are made in stainless steel, but that can lead to pollution in the material. And also, obviously, the part replacement needs to be fast. So the first trials were made internally. We actually used it for our own production of ceramic powders. And we started even in the lab. This is what you see here. So we decided to replace a stainless steel impeller blade by a ceramic one, which allowed us to modify a bit the shape and the size of the impeller, and to make it in zirconia. Zirconia is a very high wear and corrosion-resistant material, and that allows us to steer very corrosive, very aggressive suspension without any risk of pollution. Also, the savings on cost and time, if you compare it to a part who would have been prepared on demand in ceramic, is very significant. It's really, I mean, even having a quote for one part in ceramic is sometimes very hard. So having it delivered is very long and quite expensive. The third use case is we have with Avignon Ceramique. Avignon Ceramique is a very well-known manufacturer of casting cores in ceramic, mainly for aerospace industry. But here they had a requirement from a few of their customers for something a bit different. It's not a casting core, it's actually a flow sensor, a high temperature flow sensor. And the part itself is quite simply impossible to manufacture by traditional ceramic process. Why? Because you have a lot of internal channel. Here you can see the principle of these probes. It's a probe that allows you to measure the speed of a flow by measuring the difference between the static pressure and the dynamic pressure. And for that, you have a hole in front of the probe, which you can't see on the picture, I'm afraid, which goes in one of the two channels, and then 4 holes on the side of the part, which goes in the second channel, and you measure the difference in pressure between those two. That's obviously a relatively shape, actually, but just impossible to manufacture by traditional processes. And why do we need it in ceramic? Well, for high temperature. If you do a standard, it's called a pitot probe. It's usually done in metal. It's done by assembling, welding, that kind of process. But this is not possible if you need to go to high temperature. Here are some actual pictures of parts printed by Avignon. I think some people from Avignon are here, so I can thank them directly for the courtesy of giving us those pictures. You can see some kind of flow sensor probe with a few specificities. The first thing is it was made with obviously some internal channels. It was made in a hollowed out structure, which is better for thermal shock. It was made in alumina, which can withstand very high temperature. And we could even add some more complex parts with some more holes, potentially some cooling, heating circuits. Anything is possible. And on the bottom, you can see that it was inspected by dye checking, because obviously this part needs to be perfectly dense with no defects and no cracks. And the last use case here is for watch prototyping. It could be used actually for any kind of prototyping. We do have quite a few of our historical customers who are using traditional processes for ceramic. Usually it's injection molding or pressing, to make it simple, which is really amazing process for high quantity of parts. We are really not believers of the replacement of this process by 3D printing, because for high volume they are extremely effective. But when you need to do small quantities, it's much more complex, because you need a mold, actually, you need a tool. And these molds for injection molding, they're quite expensive. They start usually at a few thousand euros. They can go up to 10, 20, or even more, depending on the complexity of the part. Which leaves a gap. That means when you need to make small quantities or when you need to make prototypes, you don't know how to do them. So you can use other process, of course, but 3D printing would be very convenient. So this is what our customers do. They use 3D printing, Zetamix, to print new designs of watch and jewelry, usually in black and white zirconia. Obviously, you can see the layers here, so it's far from perfect. It's absolutely unacceptable in terms of surface finish. We have a lot of finishing to do. Some of it is often manual. We do some what we call some green finishing, so some surface treatment before sintering, which is manual labor. It would not be acceptable for production, but for prototyping, it's perfectly acceptable. And it allows to iterate very quickly. It allows to test more designs. If the designers are not sure of what they want, they can test 5, 10, 20 designs, and they can iterate very quickly before they decide which part should go in production. That's it for my examples. Thank you very much for your attention. I'll take some questions if you have some. I would just like to add that we are planning some other webinars during this period of this incredible period where we must stay at home. So if you want to keep informed about this, you can follow us on LinkedIn so that you know about the next sessions. And now I can answer to your questions.
Thank you very much for this interesting presentation. Very understandable with specific application use. We have some questions from our attendees, and I will read them for you. So the first one, do you have a mix with a fused silica?
I saw this one while I was presenting. The short answer is unfortunately no, or let's say not yet. This is something of interest because fused silica has some great application, especially because of the low thermal expansion coefficient. So we have it in mind, but let's say our pipe of R&D is quite full at the moment, so it's not supposed to be launched in the near future. However, if some of the people attending are interested in that, they can definitely get in contact with me, and we are open to discussions on that.
Okay, thank you. Another question, do you have homogeneous shrinkage at every direction, or is there a difference between XY shrinkage and Z shrinkage?
So this is a question we have quite often, and the answer is a bit complicated. If you look roughly at it, the shrinkage is homogeneous in the three directions, but it may depend on the part you're printing, on the size of the part, and also on the printing parameters. The layer size, for instance, can have an influence on that, which means that quite often there's a bit of trial and error involved here, which is that the first part is printed, checked for dimensions, and if we are a bit outside of the range, we can print the second one by correcting this difference in shrinkage, which can be done in the slicer. You don't need to modify the file, you can just change the dimensions in the slicer, which is quite convenient.
Another interesting question, you mentioned 2 nozzles for printing. Can you use the second one for printing a different compound, ceramic or metal, or the same ceramic with a different color?
So that's something we do have in mind. We have a lot of projects where we're talking about multiple material printing. Would be very attractive, but it is quite complex. But printing is not going to be a problem. I mean, printing with 2 materials, easy, no problem. The problem is going to be afterwards. It's how do you sinter that? And how do you manage so that the part stays in the right dimensions without any kind of distortion, cracks, fracture, and that's really very complicated. There's a few elements here. The first thing is all materials are not compatible. Because even if you manage to co-fire 2 materials, if they don't have the same CTE, that means the coefficient of thermal expansion, once you cool down the part, there will be differential shrinkage in the part, and you're going to end with a cracked part. So the first thing is you would need to print materials which have exactly the same CTE. One idea may be to print the same material with 2 colors, so typically black and white zirconia, since we have them. And we have a few customers in luxury which are interested in that. For the moment, it's not possible because the shrinkage of our 2 zirconia is not the same. I see the question was also asked. So for the moment, it's not possible because they don't have the same shrinkage.
We're working now on this subject, right?
We have some discussions with potential customers. The subject being quite complex, we haven't started tested because we need a real end user behind that, and it would be a big project. I mean, making multiple material printing is really not completely obvious. It is tricky.
Okay, thank you. Another question, are you limited in the design of the pieces to ensure good adhesion on the support during printing?
Well, there's always some questions about bed adhesion, and then if you have some support adhesion also. I would say that in general, so there are some rules to respect, but we do have quite a liberty in terms of design. What is the most limiting fact for design is not really the printing part, so bed adhesion or layer adhesion or whatever. It's more the debinding phase, which is really critical. And to manage to have a part which is not cracked and not deformed, which has no defect after debinding, is quite an issue, and that makes some limitation on the thickness of the part, on trying to avoid having 90-degree angles. There are a few things that in the design that needs to be adapted for the technology. But I wouldn't say that bed adhesion is the most problematic part.
And concerning printing of other materials, have you tried already to print?
I'm sorry, I didn't hear correctly.
Sorry. Have you tried to print CNC?
Again, that's a nice idea, so one that we've had in our mind for some time. If we want to print CMC, for those who don't know it, CMC means ceramic matrix composite. So that would need ceramic matrix and some fibers out of ceramic also. That should be doable, and there's two possible approaches here. The first one would be just to add in the filament some fibers, typically some silicon carbide fibers, very small ones that can go through the nozzle. That can be done. We have not tried it, but we've seen some papers from university doing it. So potentially it could be done. We could also probably print with continuous fibers. There are a few printers on the market which are equipped with a second head, which will deposit the fiber. Usually it's carbon fiber, but we could replace it with a ceramic fiber. I must say that we have not tested that for the same reason as multiple material printing. It is very interesting, but that's a complicated issue. I mean, it's far from obvious. Printing ceramic in itself, you need a bit of know-how, but printing CNC would require even more know-how. And what we are lacking for the moment is an actual application and an OEM who would be ready to either finance the R&D on that or help us finding some funds for it. If we do find an OEM who is interested in that kind of project, I would say it is doable.
Okay, thank you. Another question about the mechanical properties of your ceramic pieces.
Of course, this is also something that we have been inquired about a lot. So we have started some mechanical tests. So at the moment, I don't have the figures that I could communicate. What I can tell you in terms of the general picture is, the first thing is, obviously, we don't get the same level of properties as what you have with the bulk material. You always have a small difference because printing means between the layers you have some defects, and these defects will degrade a bit the mechanical strength. That's the first thing. The second thing is we were surprised to see that we did not see a huge difference between X, Y, and Z. For the moment, we see some difference, but not a huge difference. And the third thing is we also see that it is extremely sensitive to the printing parameters. If you print with just the right parameters, the right level of extrusion to make it plain, you may get to very high densities, more than 99%, with no level of defects. And in that case, you may have good mechanical properties. So it's still a work in progress. We're working on this with, well, we're starting to work on this with INSA de Lyon, which is going to make some mechanical tests with us. And we hope to be able to publish some paper on this before the end of the year.
You have another question concerning glass printing. Have you ever tried to print glass powder and to sinter part at low temperature, just above TG?
Again, we have not tried that. Would be of interest, especially if we could manage to make transparent glass. That would be amazing. But we haven't tried it. this is a bit hard for us, but we are being required to develop new materials all of the time because the technology is attractive. The fact that it's easy to print and it's inexpensive, and so we need to choose our next developments. This is something we have in mind: glass or quartz or silica-based material in general. We were talking about fused silica also. That would be clearly of interest, but it's not on the short list for the moment.
Okay, we have a question about the characteristic of the sintering furnace, specification and order of magnitude of the price, not of the printing, but the furnace.
Well, as I told in the presentation, we are completely based on an open system, which means that we won't force you to use our printer, we won't force you to use our sintering furnace. We can offer it, but it depends on you. If you want to use your own furnace, we're more than happy with that. And same goes for printer. Regarding the furnace, well, in terms of specs, the most important thing is temperature. If you want to sinter ceramic, you need a furnace that goes up to 1550 degrees C. Ideally, if it goes to 1600, you're quite sure that it will be able to do some cycles at 1500 before being damaged in some way. And also, a second important thing is if you want to sinter metal, you need a furnace which is compatible with that. So that means a furnace that can sinter under a neutral atmosphere. Usually it's argon or hydrogenated argon. So we do offer a system where we sell the printer and the furnace, and the full package is at 10,000 euros. So that's the starting price. It depends on the size of the size of the sintering furnace that is needed, but it's let's say good enough for parts up to 10 centimeters.
Okay, thank you. There is another question just now. Is there a notable effect of wear on the nozzle when using abrasive material? If yes, is this causing defects in the ceramic?
So yes, there is some wear on the nozzles after a while. Ceramic being very abrasive, that's an issue, and there's two ways to solve that problem. The first one is to use a wear-resistant nozzles. Some of our customers use ruby nozzles, for instance, or nozzles with a tip in ruby, and the rest being in standard brass. On our side, for the moment, we have not used such nozzles. We still use brass nozzles. What we do is just we replace it from time to time. Typically, every 1 or 2 spool or filament, we will replace a nozzle to make sure that it doesn't have any defect in terms of layer thickness or that kind of things. It may be something you want to be careful if you need really perfect ceramic with no metallic impurities, because obviously if you have some wear, that means you may have some metallic particles. So typically in the luxury industry, if you want your parts to have no metallic defects, you may want to be careful about that. You may want to use wear-resistant nozzles.
Have you ever printed aluminum silicates? And if yes, what should be the binder and firing temperature?
I must say we've never tried that. So again, as with any other material, should be doable, but I'm no expert in aluminum silicates. So I won't I won't say much more than that. Should be doable. For the moment, it's not in our top priority. Again, we're open to suggestions. So if some customers are interested in that, they can send us an email, and well, we can look into it, and we can discuss about this.
Okay, I think it was the last question. I think we can conclude now. I will thank again the speaker. Yes, we have a question about the sharing of the presentation. Yes, the speaker, Guillaume, will send to you his presentation by email. If it's okay for all of you, we will forward your email address to Guillaume DE CALAN, and he will send you his presentation. And of course, if some of you are interested in more information, we organize a technical session dedicated to Nanoe process, and it will be held in Limoges. We don't have yet the date because it should have been during April, but we have to wait now to have a meeting date where we can meet together in person. And this technical session will also be dedicated to a live demonstration, Guillaume. Also, you wanted to bring your printing machine?
Yeah, exactly. Exactly. The idea is just to show. This is one of the main interests of this technology. It's very easy to use, so we want customers to see that. So every time we do a trade show or technical sessions, we usually take a printer and we actually print on site, and that's what we would like to do. We'll also probably do that in one of our next webinars. Again, I can only suggest, but I strongly suggest that you follow us on LinkedIn so that you can be informed about these next webinars, which will probably showcase some live printing, some other use cases, and some other ideas.
Thank you, Guillaume, again very much for your presentation and your time to answer all the questions. Thank you also to all attendees for being there and asking so many questions about this very interesting FDM process. And to all of you, so see you soon, maybe for our next webinar of the Urban Cluster of Ceramics. Goodbye.
Bye.